Hello. In this video, I want to introduce a notion that's called a Freiman homomorphism, and also related notion of a Freiman isomorphism. As you will have experienced in your mathematical life, very often one introduces a new kind of object, and associated with that object will be a class of maps that are, roughly speaking, the maps that preserve the structure that you're interested in about that object. So in the case of groups, it might be group homomorphisms, and in the case of vector spaces, linear maps, and so on. So what is the structure that we're interested in additive combinatorics, or at least one of the structures? Well, we've started many statements with let A be a finite subset of an abelian group. And in general, I think one could, sometimes one's also interested in infinite subsets, but so let's just say that the basic object of study, or one of the basic objects, is a subset of an abelian group. And then from the point of view of additive combinatorics, we want to know, when do we regard two subsets of abelian groups as being essentially the same, in the sense of having essentially the same additive structure? Before I give a complete answer to that, I think I might actually just give an example or two. So here are two sets so one is a subset of z squared, so I'm just going to draw it rather than write it down. So I'm imagining that that's the point 0, 0, and this is the point 1, 0, and 1, 1, and 0, 1. So that's a subset of z squared. And now over here, I'm going to have a set of integers, which would be, say, 0, 1, and then some other numbers up here, sort of, let's say, 10, 11, or something like that. Now, if I sort of imagine myself, if I sort of draw in some vectors here, then I have a simple additive relation that if I add that vector to that vector, I'll get that vector here, but I'll draw that in too. So that minus that plus that minus that equals that minus that. Or another way of putting it actually is to say that that plus that equals that plus that. And that's actually mirrored down here, because if I think of, say, one of the unit vectors as being that, and the other one as being that, and then this diagonal vector here would be just going from here to here. And we sort of see that if I just map this point to here, this point to here, this point to here, and this point to here, then the additive relationships between these points are the same as the additive relationships between these points, except, and this is important qualification, except if I take rather large additive relations. So over here, if I take that difference there and add it several times, I eventually get to this point here. By contrast, if I take that difference there and I just add it several times, I'm never going to get to this point here, because it lives genuinely in 2 dimensions. So this looks 2-dimensional until you start looking at really high, additive relationships that involve a lot of different things. So if that were the point 10, this would be saying that 0 plus, actually we don't need to, maybe we can make it slightly more efficient, 1 plus 1 minus 0 plus blah blah blah, I'll do that 9 times, equals 10. So if I've got 9 of those, then how many terms are there in this relationship? I've got 10 ones, 9 noughts, and a 10, so that's 20 things. If I take all the minuses over to one side, over to this side, and keep the other ones over here, then I get 1 plus 1 plus 1, that's 10 of those ones, equals 10 plus 0 plus 0 plus 0, and 9 of those noughts. So I have 10 things on each side. I'll just leave that example hanging, and I will now tell you some slightly more formal definitions. So definition First of all, let's define the objects. So an additive set is a subset of an abelian group. That's all it is. And most of the time we'll be talking about finite additive sets. So let A and B be additive sets. And let phi be some function from A to B. Then phi is a Freiman homomorphism. Whoops. Too many wiggles. Freiman homomorphism of order k if whenever A1 up to AK, B1 up to BK. Sorry, it's slightly confusing my notation here, but I prefer to do it this way. So they all belong to A. The B's do not belong to B. That's a little warning there. And A1 plus A2 plus up to AK equals B1 plus B2 plus BK. We have that the same thing holds after you've applied phi to everything. So phi1 up to phi AK equals phi B1 plus all the way up to 5 BK. So it's a homomorphism of order k if it preserves sums of up to k things, or in an obvious sense of preserves. So going back to this example, this equation here is telling us that this map that took this point to here, this point to here, this point to here, this point to here, is not a Freiman homomorphism of order 10, because we can express, we've got this relationship here, 1 plus 1 plus 1, blah, 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 which is saying that plus that plus that plus that plus that equals that plus that plus that plus several times. We do not have the corresponding relationship. Oh, wait a minute, sorry. These are not Freiman isomorphic, and I haven't told you what a Freiman isomorphism is. But let's go back the other way. The map from here to here is not a Freiman homomorphism, because we've got that relationship there, but we do not have the corresponding relationship up here, because that plus that plus that plus that plus that plus many, many times does not equal that plus that plus that many, many times, whereas the corresponding relationship over here did hold. So it's not a homomorphism of order 10. It is a Freiman homomorphism of order 9, or anything less than 9. Oh, by the way, if it's a Freiman homomorphism of order k, then, and if L is less than k, then it's a Freiman homomorphism of order L, because you could just add on a few things to both sides that are the same. So I could just add A1 to both sides, k minus L times. So the larger k is, the stronger a condition this is. Incidentally, I should say that also, a few little remarks. We often refer to a Freiman homomorphism of order k as just a homomorphism of order k, or even just a k homomorphism. I shall feel free to do that. And also, the case k equals 2 is particularly important. Already k equals 2 preserves a lot of the structure that we're interested in, and quite often people will just talk about a Freiman homomorphism or between two sets. And it's because they haven't said of order k, it means that they were thinking of k equals 2. So if I don't say of order 4 or something like that, it probably means that I'm thinking of a homomorphism of order 2. I want to make a little small remark, but a rather important remark. So let's say remark. I don't think it's quite enough to call it a lemma, because the proof is too easy, but a k-homomorphism, so that's, as I say, my shorthand for a Freiman homomorphism, phi from A to B, induces, in a natural way, a k-homomorphism. Sorry, not a k-homomorphism, a map from Ka to Kb. And let's just see how that works. I could leave this as an exercise. You'd soon see that there's only one sensible map to write down, but let's just do it. So indeed, define psi from Ka to Kb by A1 plus AK maps to the only thing you can write down, really, phi A1 plus all the way up to phi AK. Now, there's a danger that this is not well defined, because A1 plus dot 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 plus AK could equal B1 up to BK, and then I'd have to say that this thing equals phi of B1 plus up to phi of BK, but that's precisely what I'm guaranteed when I know that phi is a Freiman homomorphism of order K. So let's just say this is well defined by the definition of a k-homomorphism. In the exercises, there will be a strengthening of this simple remark, which is that, and I'll just state this as a lemma, but I'm not going to prove it here. The proof is easy, but notationally a little bit tedious. So if phi from A to B is a k r plus s homomorphism, then it induces a k homomorphism from RA minus SA to RB minus SB. So proof exercise on next sheet. So not the current sheet, but I recommend doing it without, I don't necessarily wait for the next sheet to do this exercise, but it's completely clear what to write down as the definition of the map from RA minus SA to RB minus SB. You just apply phi to everything. But what you then have to do is verify that this map is a k homomorphism, and just that involves writing a lot of maybe if you're ingenious, you'll find a way of streamlining it so you don't have to keep writing complicated expressions of A1 1 plus A1 2 plus dot 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 and things like that, because you need to talk about k elements of RA minus SA. So there's quite a lot of stuff to write down. Okay, let's just have some very, very basic observations. If A is a subset of abelian group G and B is a subset of abelian group H, and phi from G to H is a group homomorphism, and I'll be quite careful to say group homomorphism when that's what I mean. So if I say homomorphism, that I will usually mean a Freiman homomorphism and not a group homomorphism. And one more condition, and if phi A is a subset of B, then the restriction of phi to A is a Freiman. I would better, just because I want to be quite careful to distinguish between what I'm talking about, is a Freiman homomorphism of order k for all k. That you can check very simply from the group homomorphism property. Let's call that basic fact number 1. Basic fact number 2, a composition, I won't even write this formally, but a composition of k homomorphisms is a k homomorphism. Any other basic facts? Some may occur to me, in which case I might sort of continue my list of basic facts. That again is a very simple exercise. I'm not going to prove it here. Now, continuing with definitions, if phi from A to B is a k homomorphism, and has an inverse, so in other words it's a bijection, that is also a k homomorphism, then phi is a, well, I'll write it out in full just this once, a Freiman isomorphism of order k. And of course I will abbreviate that to a k-isomorphism. We can go back to things like this. It's not hard to show that a composition of k-isomorphisms is a k-isomorphism. And I suppose here the analog would be if you've got a group isomorphism, and if phi A equals B, then the restriction to A would be a Freiman isomorphism of order k for all k. Back here, if I replace homomorphism by isomorphism in both places, then I again get a true statement, and here this well-defined map will be not just a map, but it'll actually be a bijection. Let's just try to justify a little bit why we should be interested in Freiman isomorphisms. So Freiman isomorphisms preserve a lot of properties that we're interested in to additive combinatorialists in additive combinatorics. So examples, 1, so let's just actually once and for all, so suppose that A is k-isomorphic to B, then 1, Ka equals Kb, size of this sum set. Perhaps I can go a little bit further. We can go sort of Ra minus Sa, the size of this difference set equals the size of this difference set if R plus S is less than or equal to K. What else could we say? 3, the additive energy of A equals the additive energy of B. So let's just see why that is. So the additive energy is counting the number of, so this one I think is simple enough, I can leave it as an exercise. In fact, they all are, but I think this one is worth just spelling out. So the additive energy is counting the number of quadruples A1 plus A2 equals A3 plus A4. But for each such quadruple, we have, if phi is our Freiman isomorphism, so this is actually just this additive energy if k equals 2, or if k is greater than or equal to 2. We get that phi A1 plus phi A2 equals phi A3 plus phi A4. There's clearly a bijection between quadruples in A and quadruples in B, and this property is preserved because phi is a homomorphism of order 2, and in the opposite direction it's also preserved because the inverse of phi is a homomorphism of order 2. So we get a one-to-one correspondence between the additive quadruples in A and the additive quadruples in B. There must be some other properties. So, and another, yes, maybe another. This is a sort of sample property. It's not a single, it's not a property that on its own is, well, it can be interesting, but it's just a sort of example of the kind of thing that one can prove. So if A contains, let's for simplicity, let's make them both subsets of Z. So if A and B are subsets of Z, and A contains an arithmetic progression of length R, then so does B. And for this we need only that K should be at least 2. So in particular for a 2 homomorphism, it preserves arithmetic progressions. And so let's just see why that is. So supposing we have a set, let's call it A plus D, A plus 2D, and so on up to A plus R minus 1D. That's my arithmetic progression of length R. So I claim that, and say phi is the Freiman homomorphism, Freiman isomorphism, I claim that phi A plus D, phi A plus 2D, up to phi A plus R minus 1D is also an arithmetic progression. And the reason for that is that an arithmetic progression in Z can be characterized by the following property, that it's a sequence A1 up to AR, such that for all I we have that for all I within a suitable range we have 2AI equals AI minus 1. It's the average of the two things on either side. I plus 1. So that's when I is from 2 up to R minus 1. So if each one's the average of the ones on the other side, you must have an arithmetic progression. If we want D to be non-zero, so some non-trivial arithmetic progression, well, that's going to be preserved because phi is a bijection. And so we need to know that, so we can rewrite this equation as AI plus AI equals AI minus 1 plus AI plus 1. And now by the definition of a Freiman homomorphism of order 2, if we apply phi to both sides, we get phi of AI plus phi of AI equals that. And that's exactly what we wanted to guarantee that this sequence is also an arithmetic progression. And obviously, if all of these belong to A, then all their images belong to B, because phi is a function from A to B. So those are a few things, a few reasons for being interested in Freiman homomorphisms. And as you'll see, it is actually not just a sort of piece of window dressing. We just go back to doing maths without mentioning Freiman homomorphisms. They are genuinely sort of things that there are proofs that would be hard to, or significantly harder to express, or ideas that would be significantly harder to express without the help of this notion. And I'm going to prove a lemma this time now, which is an example of something called a Ruzsa embedding lemma. And in the next video, I'm going to prove a more complicated Ruzsa embedding lemma. So this is the case of fp to the capital N, let's say. Now, what is a Ruzsa embedding lemma? The idea is that you take a set that has a small sum set, and so our hypothesis is actually going to be that, well, let me write it out in full. I don't think there's much point in giving an informal explanation for this one, in fact. So lemma, let A be a subset of fp to the n, and let's suppose that ka minus ka has size at most c times the size of a. So strictly speaking, I should start with let k be a positive integer and let c be a real number or something like that. Then A is k-isomorphic to a subset of a potentially much smaller. I've made no assumption at all about this capital N. It could be enormous. So it's going to be a subset of fp to the little n with p to the n minus 1 less than c times a. So that means that the size of this fp to the n is less than c times the size of a. I think it's less than that I get here rather than less than or equal to. So the idea is what I'm taking is the fp, the n I take is such that the size of this fp to the n is not much bigger than c times the size of a. And the only reason it can't just be c times the size of a is that there's just the sizes of p to the n as they jump up by a multiple of p all the time. So this could actually go up close to c times p if c happened not to be close to a power of p, or to be just slightly bigger than a power of p or something like that. So let's just have the proof. And it's a very, very nice idea. So what we're going to do is let x, in fact, it's sort of in a way, it has something philosophically in common, I think, with the idea of dependent random selection. So we're going to do a random process, but it's not sort of 100% random. So here's what we're going to pick randomly. Let x be a random subspace of capital Fp to the n of codimension n. That just means of dimension capital N minus n. Codimension little n. And let q from Fp to the capital N to Fp to the capital N quotiented out by x be the quotient map. So it takes v, let's call it 2v plus x. Now my claim is going to be that with positive probability, q is, so over here, this quotient space is just a copy of fp to the little n, because x had codimension n. My claim is with positive probability, q is going to be a Freiman isomorphism of order k. So let's just see, first of all, since Q is a group homomorphism, it is a Freiman, it's a Freiman. I better, again, since I'm talking about other sorts of homomorphisms, I'd better write this out. A Freiman homomorphism of order k. So that's part of what we want to prove. It's clearly a bijection to its image. So the only way the restriction to A can fail to be a k-isomorphism from A to QA is if there exist A1 up to AK, B1 up to BK in A, such that A1 plus up to AK does not equal B1 up to BK, but QA1 plus QAK does equal QB1 plus QBK. So you might ask, what don't we also have to think about whether we have a bijection from A to QA, but a bijection is actually the same thing as a Freiman isomorphism of order 1. Or if it weren't a bijection, I could find an A1 that didn't equal B1, but QA1 did equal QB1, and then I can just add some nonsense to both sides and get an immediate contradiction to this. So the bijection point is included in what I'm writing. So this really is the only way things can fail. And let's just think about what this second thing means. So this equality here is saying that A1 plus X plus A2 plus X plus blah, blah, blah. And when you sum up a whole lot of X's, you just get X. And similarly on this side. So it's saying that the sum of the AIs plus X is the sum of the BIs plus X, which is equivalent to saying, so let's just say, call that 1 and 2, statement 1, statement 2, but 2 is equivalent to the statement that A1 plus up to AK minus B1 minus BK is an element of X. So now let's think about what the probability is that this element is in X. So using the fact that it's non-zero. Of course, if it's 0, the probability that it's in X is 1, but we're only interested in the case where it's non-zero. So if, let's call it something else, if y in fp to the n is non-zero, then the probability that y belongs to X is, well, it's just the number of non-zero elements in X, which is p to the n minus 1 divided by the number of non-zero elements altogether, which is p to the n minus 1. And that is less than p to the minus n, because the thing on the top is smaller, so when I subtract 1, I make the whole, or from top and bottom, I make the fraction smaller. And if I didn't have those minus 1s, then it would be just equal to p to the minus n. Now, that just tells me that the probability that a single element belongs to X is sort of reasonably small. But how many elements do I have to worry about? Well, this is an element of Ka minus Ka. And indeed, every element that I have to worry about, or all the elements of Ka minus Ka will be of this form, so I'll have to worry about them. All the non-zero elements, that is. But the point is that we've assumed, haven't yet used this fact, but we've assumed that Ka minus Ka is not too big. So I bet let's just write that in. Since Ka minus Ka has size at most Ca times the size of A, it follows that if C times the size of A times p to the minus n is less than or equal to 1, then the probability that Q is a k-isomorphism i.e. probability that something bad happens is less than 1, so probably that nothing bad happens is greater than 0. So the result is proved. For any n such that p to the n is greater than or equal to c times the size of A. And we can choose such an n such that now where does this leave me? I've said p to the n minus 1 is less than c times the size of A. Yes, so if we pick the minimal n such that p to the n is greater than or equal to c times the size of A, then p to the n minus 1 is not greater than or equal to c times the size of A, so it must be less than c minus A. So picking a minimal p, also picking a minimal n, I mean. So I did state it correctly. Proves the result. Of course, that bit at the end is not the interesting part of the proof. The interesting part of the proof is just the idea of taking this random quotient map. So I'll stop there, and next time, though, I'll just tell you what I'm going to do. In the next video, I'm going to look at a subset A of Z, where I assume that Ka minus Ka has size at most C times the size of A. And what I want to do there is show that, well, what I'd like to do is show that A is k-isomorphic to a subset of some cyclic group Z over nz, where n is not too large. Actually, we'll do something a bit weaker than that. We'll show that A has a large subset that is k-isomorphic to a subset of Z over nz, where n is not too large. The proof of that is a bit more complicated than what I've just shown, but deep down it's based on the same sort of idea. But we'll see that next time.